given our discussion of the formal mathematical structure of quantum mechanics, let's think about the uncertainty principle. Usually we're talking about something like delta x, delta p is greater than or equal to h bar over 2 under those circumstances, but can we do better? Can we expand this beyond simple position momentum uncertainty? The linear algebra structure of quantum mechanics gives us a way to do that. What we're talking about here basically is the uncertainty in some observable quantity. Now, I'll leave it general and say q here, meaning we have some sort of a Hermitian operator q hat that we can use when we're talking about making measurements. The uncertainty in that physical quantity, usually expressed as the variance, sigma sub q squared, is expressed as an expectation value. So this outer pair of angle brackets is our usual usual notation for expectation value. What we're computing the expectation of is a quantity that's squared. So this is the mean squared deviation from the mean, q hat minus the expectation of q. Now this looks a little bit odd. We have one pair of angle brackets giving us the expectation of q. That's just some sort of a number. We can determine that before we even start computing. And then we have the outer pair of angle brackets that's going to give us the expectation of this overall expression, q minus the expectation of q. Let me simplify the notation a little bit here and write this number as just mu sub q. So this is the mean of q. So this is the deviation from the mean squared. This is the average mean squared deviation. That's our normal definition of the variance. Now you can expand this out using our notation for things like expectation values in the linear algebra structure of quantum mechanics. We have some sort of a wave function, q hat minus mu q squared, acting on the wave function. So this, as an operator, we've got the operator q, we've got the operator mu q. Mu q treated as an operator just multiplies by mu. It's like saying 6 as an operator. It's just going to multiply the wave function by 6. You can expand this out, psi on the left, q hat minus mu q, q hat minus mu q, acting on psi. And at this point, you can look at this and say, well, q, as represented by q hat in quantum mechanics, this q hat is going to be a Hermitian operator since we're talking about an observable q. And Hermitian operators can act either to the left or to the right. So let me take this q hat minus mu q, also, of course, going to be Hermitian because this is going to be a real number. This is going to be a Hermitian operator. The difference is just going to behave itself as a Hermitian operator. Let's have this one act on the left, leaving this one to act on the right. What I get then is going to be the result of having q hat minus mu q act on the left, inner product with the result of having q hat minus mu q act on the right. So this is just a sort of straightforward manipulation of the expression for the uncertainty in some observable quantity q. Now, you've got the same sort of thing on the left as on the right. Let's look at this and let's say this is some vector f. And this is, well, then it's going to be the same vector f. This overall here is going to act as just an inner product. F inner product with itself. I've got these two variables, or this vector which happens to appear twice. So whatever this vector is, I hesitate to call it the state of the system, but it is a vector in the Hilbert space as a result of applying a Hermitian operator to a state. And you can write that down. Just this is a definition of f. Now, in the context of uncertainty principles, we can always have determinate states. Any of the eigenvalues of q, or eigenstates, of this Hermitian operator q are going to have certain value of q. So it's certainly possible for sigma sub q to be equal to 0. But if we have a second observable, that's where we start talking about uncertainty principles. So suppose I have a second operator, or a second observable quantity r, as represented by some Hermitian operator r hat. I can use that to construct sigma sub r squared in exactly the same way as this, substituting r for q everywhere in this expression. And when you get down to it, instead of calling that f, let me call that g. So if we have two separate operators, there's nothing to prevent me from making this manipulation for both of them, which means what we're talking about in the language of the uncertainty principle, as motivated by that delta x delta p structure, we're talking about something like sigma q squared, sigma r squared. That's going to be equal to, well, it's this f inner product with itself, g inner product with itself, just multiplied together. This is sigma q squared, this is sigma r squared, this is sigma q squared, this is sigma r squared. That should be fine. So what can we do with this? We've got f and we've got g. This is where things get a little bit subtle, but the overall derivation here is not terribly mathematically complicated. You just have to pay attention as things go past. So we've got this sort of expression. What can we do with it? There are two simplifications that are going to turn this equality into an inequality and convert it into a form that is useful from the perspective of the uncertainty principle. The first of those simplifications, working with this f(f)g(g) expression for two general vectors in our Hilbert space, f and g, is the Schwarz inequality. Now, the Schwarz inequality is just a relationship between any sort of vectors like this. It says that if I've got the inner product of a vector with itself multiplied by the inner product of another vector with itself, that inner product is always going to be greater than or equal to the absolute magnitude of the inner product of the vectors with each other squared. You can think about this inequality very simply from the perspective of three-dimensional vectors in three-dimensional space. The inner product then is the dot product, and what this tells you is that the dot product of two vectors squared, a dot b quantity squared, is always going to be less than or equal to the magnitude of a squared times the magnitude of b squared. And if you're used to thinking about vectors like a dot b in the normal sort of notation, you've probably seen the formula magnitude of a, magnitude of b times the cosine of the angle between them. Now, since we're working in an infinite dimensional vector space, things like the angle between them is somewhat difficult to define, but this is the same sort of expression. If I dropped the cosine and made this into an inequality, meaning the right-hand side without the cosine is always going to be greater than or equal to the left-hand side, and then I were to say square both sides here, you would end up with the same sort of overall expression. Magnitude of a squared, magnitude of b squared, magnitude of dot product squared. So that's just an analogy. The Schwarz inequality holds in general, though it's somewhat difficult to prove. The textbook doesn't even bother proving it. So this is the first sort of simplification. We're going to pretend that instead of working with magnitude of f and magnitude of g, we're going to work with the magnitude of the inner product. The second simplification is that if we have some sort of complex number z, its squared magnitude is always going to be greater than or equal to the squared magnitude of the imaginary part of z. This is a very silly sort of construction to make if you think about it, but we can rewrite this in the context of that complex number z. So the complex number z then is always going to be at least greater than or equal to the imaginary part of z. Now the imaginary part of z, where the z is this complex number f inner product with g, we can write that as f inner product with g minus g inner product with f. So this is that number z minus its complex conjugate. Now minus the complex conjugate just flips the sign on the imaginary part, leaving the real part unchanged. So this subtraction is going to cancel out the real part and double the imaginary part. Now if I think about this, this is actually twice the complex part of this number, f inner product with g. So I would have to divide it by 2. And the imaginary part is, of course, going to be a purely imaginary number. So if I divide it by 2i, I'll get a purely real number, and I can stop worrying about the absolute magnitude. This is going to be a result. This result is essentially the same as this. So I have 1 over 2i dividing the difference of a number and its complex conjugate to pull out the imaginary part, cancel out the i, and then I'm squaring the result, same as I would be squaring the result here. So this sort of simplification, putting the overall expression up, tells you what we started with, which was sigma q squared, sigma r squared, is going to be greater than or equal to that final result. 1 over 2i times the complex number f inner product, or sorry, complex vector f inner product with complex vector g minus inner product of complex vector g with complex vector f. So, somewhat complicated expression, and unfortunately it's going to get worse before it gets better. Let's take a close look at what these vectors represent. Keep in mind that our vector f here was defined to be q hat minus mu q, acting on our state psi, and complex vector g was defined to be operator r minus mu r, acting on our state psi. Those were our definitions. So writing this out, let's take this first term first. We've got f inner product with g. That's going to be written out in terms of these definitions. So this is q operator minus mu q, acting on state psi, on the left, inner product with g, which is vector operator r minus mu r, acting on state psi. Now these are Hermitian operators, which means I can take the one that's acting on the left and push it back over to the right. Now that seems a little bit strange. Didn't we just do that step in reverse earlier on? Yes, we did. But it's a Hermitian operator. It's a perfectly valid mathematical expression. So that leaves me with just psi on its own on the left, and then we have this product of two operators, q hat minus mu q, r hat minus mu r, acting on psi, all acting on the right. This is now two binomials. It can be expanded out. So psi on the left, all by itself. And then here we've got something that needs to be FOILed. And keep in mind, operators don't commute in principle. While the operators q and r are not going to commute, mu q, r, and q, etc., those are just mu q and mu r, just multiplication by numbers. That commutes with pretty much everything. So what we're left with, we're going to have a q hat, r hat term here. We're going to have a minus mu q r hat term here. We're going to have a minus mu r q hat term from here. And we're going to have a plus mu q mu r term here. So there's our smiley face. We've counted for all of our terms, got all of the signs correct. All of that is acting on psi on the right. Now this is just an operator expression with 4 terms in it, separated by addition. These are linear operators, meaning I can separate this out into 4 separate expressions. What you're going to have then is going to be psi, q hat, r hat, acting on psi, minus mu q can be factored out of this sort of resulting expression, mu q times psi acting on r hat psi, from the r hat acting on the psi, and the mu hat being factored out. Likewise, mu r psi q hat psi plus mu q mu r psi psi. So we can simplify some of these terms right away. This guy is just 1. This is the normalization integral. If our state is properly normalized, this inner product is going to be 1. And the rest of these things, these are expectation values. This is the expectation value of q hat r hat. This is the expectation value of r hat. This is the expectation value of q hat. So if I was to pull along the constants, have them all come for the ride, this is q hat r hat minus mu q, expectation of r hat minus mu r, expectation of q hat, plus mu q mu r. But r hat, that's just mu r, and q hat, that's just mu q. So I've got the expectation value of q hat r hat, whatever it is, minus mu q mu r, minus mu r mu q, plus mu q mu r. These are just scalar multiplications, they commute, so one of these is going to cancel out. Let's say that one. And what I'm left with is the expectation value of q hat r hat minus mu q mu r. So that's what I got for fg. Now fg, I've also got to work with gf. Gf is going to end up very similarly. If you think about g and f, it's going to look essentially identical to this, except q and r are going to be interchanged. So g and f here is going to give me the expectation value of r hat q hat minus, again, mu q mu r. Same sort of product of uncertainties, or product of means. So that, believe it or not, is all we need to get our main result. We have sigma q and sigma r in terms of these sorts of complex numbers, which are expressed in terms of expectation values of those fundamental operators. So if you substitute all of that back in, we had f g minus g f. That's going to be bracket q hat r hat, so expectation of qr, minus the expectation of r hat q hat. And that's it. The mu q, mu r terms are going to cancel out. They were added on regardless whether we're talking qr or rq, so when we subtract, they're just going to cancel out. You can think about this as being the expectation of q hat r hat minus r hat q hat, which this qr minus rq, you should recognize this is a commutator. So we can write this down instead as the commutator of q hat and r hat. So, our final expression then, putting all of the constants back into it, is that sigma q squared, sigma r squared is always going to be greater than or equal to 1 over 2i times the expectation value of the commutator of the operator q with the operator r. All of that squared. That is our result. That is the generalized uncertainty principle. What this tells you is that any two operators, q and r, are going to have an uncertainty relation if they have non-zero commutator. So if the two operators commute, there's nothing wrong with knowing both of them precisely. They can both have zero uncertainty. But if they have non-zero commutator, meaning the expression qr minus rq does not have zero expectation value, then any two observables then those two observables will have non-zero uncertainty principle. There will be some minimum uncertainty. The obvious example to do here is position and momentum. We talked about the commutator of the operator x hat and the operator p hat before. It's just x hat, p hat minus p hat, x hat. And if you substitute in the definition of p hat as minus I h bar partial x, and the definition of the operator x hat as just x, multiplied by, and you insert some dummy wave functions on either side, that was an activity that we did earlier on in the course, you find that the commutator here is equal to just a constant, I h bar. It's a complex constant, which seems a little strange, but there's nothing wrong with complex numbers when you're mixing operators like this. It's only when you would make an observation of a single operator, single physical quantity, that you have to get real numbers. What that tells us is that sigma x squared sigma p squared in the generalized uncertainty relation is going to be 1 over 2i times the expectation value of the commutator, which is just I h bar squared. So the expectation value of a constant is just going to be the constant. So this is just going to be I h bar over 2i quantity squared. I's cancel out, and we've just got h bar squared over 4. H bar over 2 squared. Now the way the uncertainty principle is usually stated is sigma x sigma p is greater than or equal to h bar over 2, and that of course is clearly the same expression that we're working with here. So good. We've got the same sort of uncertainty relation that we introduced earlier on in the course. To check your understanding of this sort of process, here are some questions for you. What would happen in the derivation if instead of throwing out the real part, meaning instead of saying that the absolute magnitude squared of some complex number is always greater than 1 over 2i z minus z star, all squared, what would happen if I instead threw out the real part by adding the number to its complex conjugate instead? Would you still get a commutator, and what extra terms would it introduce? And finally, just in terms of some of the steps in that derivation, why exactly did this step happen? What are the principles that are applied in that equality? What definitions do you need to know? Now that's about all that there is to the generalized uncertainty principle. It's an amazingly powerful mathematical tool, but well, let's play with it a little more. How strict is this limit, and can we beat it? Now, the limit that we're talking about here is this relationship. I had some sort of sigma q squared, sigma r squared, was always greater than or equal to 1 over 2i times the expectation of the commutator of operator Q and operator R, all squared. That's our generalized uncertainty principle. This inequality, where did that inequality come from? Well, it came from two places. It came from the Schwarz inequality, which told you that the inner product of that vector we defined, f with itself, multiplied by the inner product of the vector g with itself, was always going to be greater than the squared modulus of the inner product of f and g. That was one source of the inequality. So if we're trying to make this into an equality, we have to not grant any space in between the result of these inner products and the inner product of the vectors with itself. How can we make the Schwarz inequality into an equality, in other words? And that's rather straightforward if you think about it. The vector g is just going to be some constant, say c, times the vector f. If this is true, then this is going to be c squared f squared, and this is going to be c squared f squared, and we're going to have an equality here overall. The second inequality we had was when we threw out the real part. We said the magnitude of that complex number, fg, in terms of its squared modulus, was always going to be greater than or equal to this 1 over 2i times fg minus gf. All of that squared. This statement, can we make this into an equality as well? Well, what we're looking at here is going to be an equality if we're throwing out the real part, and we're taking the squared magnitude of it. The squared magnitude is only ever not going to change when we throw out the real part, if the real part is 0 to begin with. So we've got equality here if the real part of fg, that inner product, is equal to 0. And that's reasonably straightforward. We're looking at fg, but we know g can be expressed in terms of c, so we're talking about the real part of f times g expressed as cf gives me a c and another f. So the real part of c times this inner product of a function, or of a vector with itself, this inner product of a vector with itself is going to be a real number. No matter what you do, you're taking a complex conjugate, multiplying it by itself, essentially, you're going to get a real number. So this is only ever going to equal 0 if c is complex. C is, purely imaginary. C being purely imaginary, let's write it as the imaginary unit I times some real number, A. So given some C equals I times A, if we define our states, or if we define our operators and our states such that G is given by some complex unit times A times the state F, for some real A, then we've turned both of our inequalities into equalities. So what does that mean? What sort of implications does this have? Let's consider that in the context of position momentum uncertainty, just to make this a little more concrete. We have this notion that our vector g is imaginary unit times some real number times our vector f. Now, in the version, or in the language of position momentum uncertainty, then this vector g is going to be p hat minus expectation of p times our state. And we know what the position, or what the momentum operator is. This is going to be minus I h bar, partial derivative with respect to x, minus expectation value of p. I'll just leave it as expectation value of p here. This is just going to be a number, so there's no magic there. And this is going to be multiplied by psi of x. If I'm writing out my momentum operator in terms of partial derivatives, I better write my wave function in terms of x instead of just as some arbitrary state vector. Likewise, we've got our vector f, and this has to be expressed in terms of our position. So this is going to be x hat minus expectation of x, acting on our state. And likewise, in terms of wave functions, this is going to be x multiplication minus expectation value of x, the constant, multiplying our wave function psi of x. So our expression for G in terms of IA times F with these particular definitions of G and F, we can plug these together, substitute these expressions here into this equation here, and you end up with, separating things out, minus I h bar partial psi partial x minus expectation value of momentum multiplying psi. And that has to be equal to I times A times our expression for F, which, I'll just expand that out. We've got I times A times X times psi of X minus I times A times expectation of X times psi of X. This right here is a differential equation for psi. And it turns out it's actually a pretty easy differential equation to solve. If you rearrange things a little bit, you can find out that this is going to give you a derivative of psi with respect to x as, in terms of, let's see, what have I got? I've got a, after I've divided through by minus I h bar, I'm going to have a minus a over h bar, let's say x psi, pulling the complicated term first, and then I'm going to have a plus a over h bar expectation of x psi, and a plus I expectation of p over h bar psi. Provided I've got all of my signs correct there, and I haven't lost any terms. I've got the over h bars. Yeah, I think that looks right. This is a fairly straightforward ordinary differential equation to solve. Now I'll leave it as an exercise to you guys to actually go through and solve this, but the procedure for solving it I think is most easy to think about. Let me just guess that my wave function psi is equal to e to the some sort of function f of x. If you do that, you find a simplified differential equation just for f. This sort of initial guess where psi is going to be some sort of an exponential and you're trying to find the behavior of the exponent is a common technique for solving differential equations where your derivatives essentially give you the function back multiplied by various terms. Under these circumstances, you can figure out what your psi of x actually looks like. And your psi of x under these circumstances has to be e to the minus a over 2 h bar, let's see, x minus the expected value of x, quantity squared, e to the I expectation value of p over h bar times x. And then there's another constant floating around here, something like e to the a expectation value of x squared all over 2 h bar. This solution comes out of just a straightforward solve here. The only simplification I've made on the result is to complete the square in the exponent. Whenever you have a x squared sort of behavior, it's good to pull that off by itself. The reason I've separated these three terms out instead of writing them all as sums together in the exponent is it makes the structure a little bit more straightforward. This is some sort of a constant. This is something that looks like just something with a certain momentum, ikx. And this is a Gaussian. E to the minus something x squared. This Gaussian form is definitely a realizable wave function. We've actually met Gaussian wave functions before, for example, in the quantum harmonic oscillator ground state. Under those circumstances, you have met the uncertainty limit. You can meet the uncertainty principle limit, so the two messages there is that, first of all, the uncertainty limit is attainable, but it's difficult. You have to be in a very specific sort of mathematical state. This is not going to be true for anything that's non-Gaussian. The second take-home message from this is that the uncertainty principle is actually a fairly strict limit, that despite the fact that we made those seemingly a little bit fudgy simplifications when we were working through the derivation of the generalized uncertainty principle, applying the Schwarz inequality, and just assuming that the real part of the number could be neglected and the imaginary part was the only thing that mattered, we haven't actually ceded too much ground there. The uncertainty principle is a fairly strict limit that is actually attainable. It's not like we've made some ridiculous lower limit, or ridiculous lower limit on the uncertainty. Regardless, that's a mathematical discussion of the formal structure of the uncertainty principle in quantum mechanics, and subject to the generalized uncertainty principle, any two operators with a non-zero commutator are going to have some sort of uncertainty principle. And you could go through the same sort of derivation of what the minimum uncertainty behavior would look like for any two operators. It's relatively straightforward for the position momentum structure, and you get a Gaussian, but you could do it for other cases as well. I think that about sums it up, though. Generalized uncertainty in quantum mechanics is, like I said, a very powerful mathematical tool, so keep that one in your bag of tricks. Deviation from the mean squared. This is the average mean squared deviation. That's our normal definition of the variance. Now you can expand this out using our notation for things like expectation values in the linear algebra structure of quantum mechanics. We have some sort of a wave function, q hat minus mu q squared, acting on the wave function. So this, as an operator, we've got the operator q, we've got the operator mu q. Mu q treated as an operator just multiplies by mu. It's like saying 6 as an operator. It's just going to multiply the wave function by 6. You can expand this out. Psi on the left, q hat minus mu q, q hat minus mu q, acting on variance, sigma sub q squared, is expressed as an expectation value. So this outer pair of angle brackets is our usual usual notation for expectation value. What we're computing the expectation of is a quantity that's squared. So this is the mean squared deviation from the mean, q hat minus the expectation of q. Now this looks a little bit odd. We have one pair of angle brackets giving us the expectation of q. That's just some sort of a number. We can determine that before we even start computing. And then we have the outer pair of angle brackets that's going to give us the expectation of this overall expression, q minus the expectation of q. Let me simplify the notation a little bit here and write this number as just mu sub q. So this is the mean of q. So this is the deviation psi. And at this point, you can look at this and say, well, q, as represented by q hat in quantum mechanics, this q hat is going to be a Hermitian operator, since we're talking about an observable q. And Hermitian operators can act either to the left or to the right. So let me take this q hat minus mu q, also of course going to be Hermitian, because this is going to be a real number, this is going to be a Hermitian operator. The difference is just going to behave itself as a Hermitian operator. Let's have this one act on the left, leaving this one to act on the right. What I get then is going to be the result of having q hat minus mu q act on the left, inner product with the result of having q hat minus mu q act on the right. So this is just a sort of straightforward manipulation of the expression for the uncertainty in some observable quantity q. Now, you've got the same sort of thing on the left as on the right. Let's look at this, and let's say this is some vector f, and this is, well, then it's going to be the same vector f. This overall here is going to act as just an inner product. F inner product with itself. I've got these two variables, or this vector which happens to appear twice. So whatever this vector is, I hesitate to call it the state of the system, but it is a vector in the Hilbert space as a result of applying a Hermitian operator. Given our discussion of the formal mathematical structure of quantum mechanics, let's think about the uncertainty principle. Usually we're talking about something like delta x, delta p is greater than or equal to h bar over 2 under those circumstances, but can we do better? Can we expand this beyond simple position momentum uncertainty? The linear algebra structure of quantum mechanics gives us a way to do that. What we're talking about here basically is the uncertainty in some observable quantity. Now, I'll leave it general and say q here, meaning we have some sort of a Hermitian operator q hat that we can use when we're talking about making measurements. The uncertainty in that physical quantity, usually expressed as the variance,